Two countries, two aircraft programs, the exact same underlying problem. Russia named theirs the MC-21. China named theirs the C919. Both were built with one clear ambition in mind: to finally challenge the decades-long grip Boeing and Airbus have held over commercial aviation. Both aircraft featured genuinely modern designs, serious engineering talent, and real national ambition behind them. And both of them, on the very day each first took to the sky, had someone else's engine bolted underneath the wing. That is not a coincidence. That is actually the whole story of what happens when a country is capable of building a great airplane, but still cannot build the one single component that lets that airplane fly entirely on its own terms. And by the time we reach the end of this video, you'll understand exactly why Russia, China, and the West are all quietly fighting the same underlying war, just from very different fronts. Before we go any further, here's a question worth sitting with for a second. If a country can copy an entire airplane, why can't it just copy the engine too? Some early Soviet-era airliners visibly borrowed design cues straight from Boeing's early jets. China's J-11 fighter is essentially a licensed reproduction of Russia's Su-27. Airframe knowledge has always crossed borders fairly easily throughout the entire history of aviation, always. So why doesn't the same thing happen with engines? Here's the short answer you need to hold onto for the rest of this video. An airframe is fundamentally a geometry problem. An engine is 30 years of accumulated knowledge that simply doesn't exist anywhere you can actually see it. Russia, 2013, deep in the Ural Mountains near Perm, a team of engineers at Aviation, Russia's oldest engine design bureau, begins final development work on the PD-14, a completely new turbofan engine and Russia's first genuinely clean sheet commercial engine design since the Soviet era ended. That same year, in China, in Shanghai, a separate team at AECC Commercial Aircraft Engine begins serious development work on the CJ1000A, China's very first domestically designed commercial turbofan engine ever in the country's entire aviation history. Two engineering teams, two completely different cities, two countries that had already spent decades successfully designing world-class airframes, and both were only now confronting the exact same uncomfortable realization. They could not simply do for engines what they had already managed to do for wings. Here's why that gap exists. An airframe, at its most fundamental level, is a geometry problem. The right curve along the wing, the right angle on the tail, the correct skin thickness at different points along the fuselage. Difficult to get right? Absolutely. But ultimately, it's a problem of shape, and shape can be observed, measured, photographed, and reverse engineered by a determined enough team with the right resources. That's a large part of why certain early Soviet jets ended up visibly resembling Boeing's designs. That's why the J-11 so closely resembles the Su-27 it was derived from. Airframe knowledge travels between countries precisely because you can actually look at it and study it from the outside. Now compare that to what's happening inside a modern jet engine. Temperatures inside the hot section of a modern turbofan can reach up to around 1,600 degrees Celsius. Steel melts at roughly 1,270 degrees Celsius. In other words, the air moving through that engine core is genuinely hotter than melting steel. And the turbine blades spinning directly inside that punishing heat have to survive it, not just for a single dramatic hour, but reliably for something like 30,000 hours of continuous commercial flight operation across the aircraft's working life. You simply cannot photograph that kind of process. You can't reverse engineer it just by looking at the finished part sitting on a table. That knowledge lives inside proprietary metallurgy labs, inside decades of accumulated testing data, inside an understanding that was painstakingly built, failure by failure, over generations of engineers who each inherited lessons the last generation learned the hard way. To really appreciate just how much sits behind those turbine blades, it helps to understand what they're actually made from. Modern high-pressure turbine blades are typically cast as single crystals, meaning the entire blade is grown as one continuous, uninterrupted lattice of metal with no internal grain boundaries at all, because grain boundaries are exactly where cracks eventually start under that kind of extreme heat and stress. Growing a single crystal blade reliably, at scale, with consistent quality across thousands of units, is itself the product of decades of specialized foundry work that only a handful of companies on the planet have ever fully mastered. On top of that casting process, the blades are then coated with thermal barrier coatings, only a few hundred. Microns thick, layers of ceramic material engineered to survive repeated thermal cycling without flaking or cracking, while internally the blades are riddled with microscopic cooling channels that pump air through the metal itself just to keep it from melting in place while the engine is running. None of that shows up in a photograph of the finished engine. All of it lives inside institutional knowledge that took entire careers, and in some cases entire generations of engineers, to accumulate. That difference right there is exactly what makes engine independence matter so much more than airframe independence ever could. And that's precisely why, back in 2013, both Russia and China found themselves starting their respective engine programs from nearly zero, not because either country lacked ambition, and certainly not because they lacked capable engineers. It's because this particular category of knowledge simply cannot be borrowed, cannot be bought outright, and cannot be casually copied from a photograph. It can only be built slowly from the ground up, one hard-won failure at a time. So here's the natural follow-up question. If an engine genuinely cannot be copied the way an airframe can, what does a country actually do in the meantime? While it's still busy building one of its own, it uses someone else's engine instead. And that's exactly where things start getting complicated, both technically and geopolitically. It's worth pausing here to understand just how few countries have ever actually crossed this particular finish line. Right now, only a small handful of nations on Earth can genuinely design, build, and certify a modern high-bypass commercial turbofan engine entirely from scratch, without leaning on outside licensing or shared design work. The United States can do it. The United Kingdom can do it, largely through Rolls-Royce. France can do it, largely through Safran, often in partnership with General Electric. That's essentially the entire list of countries capable of doing this completely independently, and it hasn't meaningfully expanded in decades. Japan, despite building some of the most advanced precision manufacturing in the world, still doesn't field a complete commercial engine of its own from a clean sheet. Germany, despite deep aerospace expertise through companies like MTU Aero Engines, participates as a partner on international engine programs rather than fielding a fully independent design. That short list should tell you everything about just how difficult this particular technology actually is to master from zero, and it's exactly the club both Russia and China are now trying to force their way into. Russia, 2017. The MC-21 makes its first flight. It arrives with modern composite wings, a noticeably wider cabin than its closest Western rivals, and on paper, seemingly everything it needs to seriously compete with the Boeing 737 MAX and the Airbus A320neo. But hanging underneath those wings sit Pratt & Whitney PW1400G engines, American-made engines. Russia had successfully designed and built the entire airframe on its own, yet the aircraft still depended completely on another country for the single component that actually made it fly. Its own domestic engine, the PD-14, simply wasn't ready for prime time yet. That same year, China found itself facing a somewhat different version of the exact same underlying problem. For years already, China had been purchasing AL-31F engines from Russia to power its J-20 stealth fighter program. Russia was perfectly willing to sell China engines, but notably not its very best ones. The specific engine variants delivered to China were consistently older and less capable than the versions Russia kept reserved exclusively for its own Air Force. This, it turns out, is exactly what technological dependence often looks like in practice out in the real world. It's rarely ever a flat, outright refusal to sell anything at all. Far more often, it quietly shows up as a limit instead. We'll happily sell you an engine, just not that particular engine. The real-world consequences of that limit became obvious inside the J-20 itself. The aircraft had originally been designed with supercruise in mind, meaning sustained supersonic flight without needing to burn extra fuel through afterburners, widely considered one of the defining hallmark characteristics separating a true fifth-generation fighter from everything that came before it. Instead, in practice, the aircraft ended up relying heavily on its afterburners, far more than intended, not because the airframe itself was somehow incapable of achieving that performance envelope, but because the engine actually available to power, it simply couldn't deliver the thrust needed without help. China had the airframe, the sprawling factories, and the skilled pilot S, all ready to go. But Russia still quietly controlled the underlying technology that ultimately determined just how much of that aircraft's real potential could actually be unlocked in practice. And that reveals the second, deeper layer sitting underneath this entire story. Successfully designing a genuinely world-class aircraft is really only half of the challenge. If another country still controls the engine underneath it, that country ultimately controls the outer limits of exactly how well that aircraft can ever actually perform. The airframe determines what is theoretically possible on paper. The engine determines how much of that theoretical possibility actually becomes real, usable performance out in the field. This same pattern, incidentally, shows up again and again across the history of Chinese military aviation, not just with the J-20. Earlier fighters, like the J-10, spent years flying with Russian-supplied AL-31F engines before China finally managed to field its own domestically produced WS-10 engine in sufficient numbers and reliability to fully replace the imported version. Each time, the underlying story followed the exact same arc. China would design a genuinely capable airframe well ahead of schedule, only to then spend years working around an engine gap that no amount of airframe engineering talent alone could ever fully close. It's a pattern so consistent across multiple aircraft generations that it stopped looking like bad luck a long time ago and started looking like a structural feature of how aerospace development actually works. Russia, for its part, would go on to learn an even harsher version of that exact same lesson just a single year later. By 2018, as Western sanctions against Russia continued steadily tightening across multiple industries, the long-term future of the entire MC-21 program became increasingly uncertain almost overnight. Pratt & Whitney simply could not keep supplying PW1400G engines, indefinitely under mounting U.S. government restrictions, regardless of what either company actually wanted commercially. The very same American engine that had originally helped launch Russia's most advanced commercial aircraft program in decades could just as easily become the exact reason the entire program stalled out completely. What followed was several genuinely difficult years of rebuilding almost from scratch. The original American-powered MC-21 airframes were effectively grounded, the Pratt & Whitney engines were physically removed, and the entire aircraft was carefully redesigned around Russia's own domestically produced PD-14 engine instead. Only after several more years of rigorous testing, painstaking certification work, and careful systems integration did the program finally return to active flight testing with an aircraft that Russia could now produce, start to finish, without relying on any foreign engine supplier whatsoever. That stark contrast right there is exactly why engine technology ends up mattering so enormously much in stories like this one. It's worth appreciating just how expensive and slow that entire re-engining process actually turned out to be in practice. Swapping an engine on a certified commercial aircraft isn't remotely as simple as unbolting one unit and bolting on another. The engine mounts, the wing structure surrounding them, the fuel systems, the electrical wiring, the flight control software, even the aircraft's overall weight and balance calculations. All of it has to be re-engineered and revalidated around the new engine's specific dimensions, weight distribution, and thrust characteristics. Then, the entire aircraft has to go back through extensive ground testing and flight testing all over again before regulators will sign off on it as airworthy. For the MC-21, that entire process reportedly added years onto the program's original timeline and pushed its full commercial rollout back substantially from what Russia had originally announced. It's a very concrete illustration of exactly why the earlier point about dependency being baked directly into the airplane's own DNA isn't just a turn of phrase. It's a genuine engineering and financial reality that can delay an entire national aviation program by the better part of a decade. By the way, if you genuinely enjoy going beyond the usual surface-level headlines to actually understand the underlying technology, the strategy, and the geopolitics quietly shaping global aviation behind the scenes, go ahead and subscribe to the channel. That's really the entire mission behind every single video we publish here. Because the third layer of this story is where things get genuinely uncomfortable, and not just for Russia, and not just for China either. This layer reaches all the way into Boeing and Airbus's world too. Washington, D.C., May 2025. The U.S. Department of Commerce suspends export licenses covering the engines that power the C919. COMAC, by that point, had already spent roughly 15 years of sustained effort building that entire aircraft program from the ground up. It had a functioning factory in Shanghai, a fully certified aircraft design, and more than 1,000 firm orders already, locked in from various Chinese domestic airlines. The production line was actively running at pace. The working relationship with the foreign engine supplier had, up until that point, been functioning exactly as intended for years. Then, almost without warning, the export licenses were abruptly suspended. Nothing had actually gone wrong on a purely technical level. No safety issue, no mechanical failure. A single administrative document had simply been withheld, and along with it, access to the one critical component COMAC still could not manufacture entirely on its own. China had originally planned to deliver 75 completed C919 aircraft that particular year. In the end, it managed to deliver just 15. Nothing about the aircraft itself had changed in that window. What changed entirely was access to the engine sitting underneath its wings. It's genuinely worth sitting with how strange that gap looks on paper, 75 planned deliveries collapsing down to just 15, without a single design flaw, safety issue, or manufacturing defect anywhere in the picture. Every other part of the supply chain, the airframe structures, the avionics, the interiors, the domestic assembly line in Shanghai, kept functioning exactly as planned the entire time. 60 aircraft's worth of production simply had nowhere to go, sitting short one component that COMAC still could not build for itself. That's an unusually clean, almost clinical demonstration of just how completely a single supply chain bottleneck can throttle an entire national industrial program, even when every other part of that program is executing flawlessly. The suspended export licenses were eventually reinstated roughly 2 months later, and production activity gradually resumed after that. But by then, the underlying lesson had already been quietly written down for the entire global aerospace industry to absorb. It's worth putting that engine specifically in context, too. The C919 flies with LEAP 1C engines developed by CFM International, itself a joint venture between America's GE Aerospace and Francis Safran. That single joint venture engine also happens to power large portions of the competing Boeing 737, MAX and Airbus A320neo fleets, which means COMAC's dependency wasn't on some obscure niche supplier operating at the margins of the industry. It was on the exact same engine family that keeps roughly half the world's single-aisle commercial fleet flying every single day. In some ways, that made the arrangement look reassuringly stable, right up until it very suddenly wasn't, precisely because an engine embedded that deeply into the global supply chain felt, at least on paper, far too systemically important to ever actually get interrupted. It served as a stark reminder that this kind of dependence doesn't only become genuinely dangerous the moment another country flatly refuses to sell you something. Sometimes it becomes dangerous precisely because everything appears to be working perfectly smoothly, right up until the exact moment it suddenly isn't. That distinction is really what separates this particular story from everything that came before it in aviation history. Russia learned the hard way what happens when another country simply won't sell it the specific engine it actually wants. China learned a subtly different lesson: what happens when another country remains perfectly willing to sell you an engine, right up until the precise moment it unilaterally decides not to anymore, with very little warning. One form of dependence is at least visible and predictable well in advance. The other form can interrupt an entire aircraft production program essentially overnight, without any real warning at all. It's worth noting that COMAC wasn't entirely unprepared for this exact scenario, even if the timing still caught the program off guard. China had already been quietly developing its own domestic alternative to the LEAP 1C for years through the CJ-1000A program, precisely because Chinese planners understood, at least in the abstract, that relying on a foreign-controlled engine for the country's flagship commercial jet carried exactly this kind of systemic risk. The May 2025 suspension didn't create that motivation out of nowhere. It simply confirmed, in the most concrete way possible, why the motivation had existed in the first place. Every delivery shortfall that year became a very public, very expensive advertisement for finishing the domestic engine program as quickly as possible, and it's reasonable to assume that episode alone did more to accelerate internal funding and political urgency behind the CJ-1000A than any strategy document ever could have. Now, it's worth being clear that this particular vulnerability isn't remotely unique to Russia or China. For years, Boeing reportedly sourced somewhere around 80% of its aerospace-grade titanium from Russia's VSMPO Avisma, while Airbus relied on that very same supplier for somewhere around 60% of its own titanium needs. The underlying strategic principle at play there is exactly identical to everything we've already discussed. Whenever a critical piece of technology or a critical raw material comes from somewhere else entirely outside your own borders, that outside supplier automatically gains real leverage over you, whether either side ever explicitly acknowledges it or not. The meaningful difference is that titanium, unlike a fully certified jet engine, actually has viable alternatives available. Other countries mine titanium ore. Other companies around the world process and refine it into usable aerospace-grade material. Over the past several years, Airbus in particular has been steadily working to reduce its reliance on Russian titanium, specifically by deliberately developing and qualifying new alternative suppliers elsewhere. A fully certified commercial jet engine, by comparison, offers absolutely no such convenient flexibility. Once a specific aircraft has already been designed, tested, and formally certified around one particular engine type, swapping that engine out for a different one requires years of expensive redesign work, full regulatory recertification, and extensive new flight testing all over again from the beginning. The dependency, in a very real sense, ends up permanently built directly into the airplane itself, baked into its DNA. There's actually a broader pattern hiding inside this titanium comparison that's worth pulling out explicitly. Raw materials like titanium sit at one end of a long spectrum of technological dependency. They're valuable, strategically important, and genuinely worth diversifying away from. But at the end of the day, they're still commodities that multiple suppliers around the world can eventually learn to produce to the same specification. A finished, certified jet engine sits at the completely opposite end of that same spectrum. It isn't a commodity at all. It's the end product of an entire ecosystem of specialized knowledge, proprietary alloys, decades of flight hour data, and regulatory trust built up over generations between a manufacturer and aviation authorities like the FAA and ASA. You can eventually replace a titanium supplier. You cannot meaningfully replace an entire engine ecosystem without effectively rebuilding an entire national aerospace industry from the ground up, which is precisely the multi-decade project both Russia and China now find themselves in the middle of. And that's ultimately why engine independence matters so much more, strategically, than airframe independence ever really does on its own. An airframe genuinely enables a country to design its own aircraft from scratch, but an engine gives that same country the actual ability to keep building and operating that aircraft indefinitely, on its own terms, without needing anyone else's permission. One capability represents pure engineering skill and design talent. The other represents something closer to genuine strategic sovereignty. And that, right there, is really the honest answer to the exact question this whole video opened with. Because, fundamentally, an airplane that doesn't have its own domestically produced engine underneath its wings isn't truly that country's airplane at all, not in the fullest sense. It's effectively a lease, with terms quietly set by someone else entirely, renewable at their convenience, or not, entirely at someone else's discretion, in some foreign capital thousands of miles away. So here's a genuine question worth thinking about. Do you think Russia and China will actually manage to achieve true engine independence sometime within the next decade or so? Or do you think both countries will realistically remain dependent on foreign engine technology for a good while longer yet? Let me know your honest thoughts down in the comments below. I'd genuinely love to hear your reasoning either way. It's a genuinely difficult question to answer with any real confidence, and that's exactly what makes it worth asking out loud. Engine development doesn't move at the same pace as software or even airframe design. It moves at the pace of accumulated flight hours, accumulated failures, and accumulated trust from regulators who have every incentive to move cautiously. The PD-14 took the better part of a decade to go from a clean sheet design to a certified engine actually flying in revenue service, and even now it's still expanding its certified flight envelope and production volume year by year. The CJ1000A is following a broadly similar arc, with test articles running on ground stands and early flight testing already underway, but full commercial certification and mass production readiness still sitting somewhere further down the road. Whether that road takes 5 more years or 15 more years genuinely depends on variables nobody outside those two engineering programs can fully see from the outside, which is exactly why this remains one of the most interesting open questions in aviation right now. Up to this point, you can clearly see that these are two very different countries, China and Russia, sitting at noticeably different distances from the summit of true engine independence, yet both are still climbing the exact same mountain. Both of them learned this hard, uncomfortable lesson very publicly, in ways the entire global aviation industry was watching closely in real time, learning exactly what happens the moment someone else quietly holds the engine underneath your own aircraft. And whichever country ultimately manages to finish building its own engine entirely on its own terms, answering to absolutely nobody else's foreign export control regime, won't simply end up with a working engine at the end of that long road. It will possess the one genuine asset in all of commercial aviation that can never be casually taken away by a single signature stroked in some foreign capital thousands of miles from home. Our next deep dive on civil aviation looks specifically at exactly how close China actually is to reaching that particular finish line. What the CJ1000A engine can genuinely do today, what it still can't quite manage yet, and what the entire global aviation market will realistically look like on the exact day it finally crosses over into full commercial service. That video is up on your screen right now. See you there in the next one.